Number 5, fine particles of metallic iron can be injected underground to remediate pollution of underground aquifers by the industrial solvent trichloroethene. In one experiment, 2,400 liters of aqueous emulsion, so this is our aquifer, containing about 480 kilograms of iron, and that has an oxidation state of 0, that's what the 0 represents, consumed 17 kilograms of trichloroethene. So the chemical formula for trichloroethene is C2HCl3. So 17 kilograms of this stuff was consumed in 5 months. And the first thing we're asked to do is identify the oxidizing and reducing agents for this reaction. And we are told it is unbalanced. So we have iron, and that's going to form iron 2. Immediately, you should be able to see that that is oxidation. Remember, oxidation is loss. So this is your reductant or your reducing agent. It is the thing being oxidized on the reactant side. Then we have our trichloroethene, C2HCl3, and that will form C2H4 and the chloride ion. So this is going to be our oxidant, and specifically it's going to be the carbon. The carbon is a +1 in this compound, and then in this compound, it becomes a -2. How do you know that? Well, hydrogen, for all intents and purposes, is going to be a +1. There are 4 of them. We have 2 carbons. Therefore, in order to make this electrically neutral, the carbon should be, I said -2. Yeah, -2. That makes sense. And in this compound, chlorine is a -1, and there are 3 of them. So we have a total of -3. The hydrogen is a +1. So now the net of this is a -2. We have 2 of these. Therefore, this is a +1 in order to balance that -2 out and make this compound make sense. So that's how that is done. So your reductant is the iron, and the trichloroethene is going to be your oxidant. The thing being reduced is the oxidizing agent or the oxidant. We're then asked to write balanced half reactions for each using water and the hydrogen ion to complete the balancing, and then write the balanced net reaction. So this is a case where we're going to use all of our steps. Let's just clean this up a little. First, we balance our atoms other than hydrogen and oxygen. So I need a 3 in front of my chlorine. Carbon is balanced. Now I'm going to look for our oxygen. I have none. And I look for hydrogen. I have 4 hydrogens here and 1 here. So I must need 3 hydrogen ions over here on the reactant side. Now I need to balance the charge. I already did the charge for the iron. So let's look at this trichloroethene business. So I have a 3 positive on the reactant side, and on the product side, I have a 3 minus charge because that's from the chlorine, 3 minus. So in order to get this to balance, I must need 6 electrons over here because that will give me a net of 3 minus, and then my charges are balanced. So now I need to balance my electrons, and in order to do that, I'm going to multiply this half reaction through by 3 because that will give me 6 electrons on the product side. So now I write the whole thing out. 3 Fe plus 6 electrons, 3 hydrogen ions, C2HCl3, and that will react to form 3 iron 2, 6 electrons, C2H4, and 3, oh goodness, that was a 3 Cl minus. So now I can cross out what's the same on both sides. And then I am left with the balanced equation, 3 Fe plus C2HCl3 plus 3 hydrogen ions. You can put those in any order as long as they're all on the reactant side, plus 3 Fe2 plus C2H4 and 3 Cl minus. So that is our balanced reaction. B, what percentage of what was injected was actually used over 5 months? Well, first, how much was actually injected? We injected 480 kilograms. That was given to us in the problem. 480, can't see it. 480 was originally injected. So how much was used? Well, we used the equivalent amount of iron to consume 17 kilograms of C2HCl3. So let's convert that into moles first. So I'm going to just change this into 17,000 grams, save me a step. And the molar mass of this is 131.39 grams per mole. Now I need my stoichiometry. So for every 1 mole of C2HCl3, I need 3 moles of iron. And then I need to know how many grams of iron that is. So I need to go to my periodic table. And a mole of iron is 55.845 grams. And then I can convert that back to kilograms. There are 1,000 grams in 1 kilogram. And I'm writing it out for the benefit of those who still need it. And I get that 21.6, I get a 676, so I would round that to 8 kilograms of iron were used. So the question asks, what percentage of injected iron was used? So this is what was used. I'm going to divide that by the total injected, which was 480, and multiply all of that by 100. And I get 4.5% was used. Now, I did use 2 significant digits there because all of my measured quantities provided up here were also 2 significant digits. And C, how much current is flowing between the reactants if trichloroethene reacts at a constant rate of 17 kilograms per 150 days. Well, I need to know, well, I get happy with the eraser, but we'll just recreate it. So how much current is flowing? We have a rate here, and that rate is 17 kilograms of C2HCl3 per 150 days. So current is measured in coulombs per second. That is what an amp is. So let's convert this into moles per second first. So I'm going to take my kilograms, and in 1 kilogram, I have 1,000 grams. You'll see that we've done most of this calculation already, but like I said, I get eraser happy. And then we have 131.39 grams of C2HCl3 per 1 mole. And let's take our days. So 1 day is 24 hours, and you can break this up any which way you need to. 1 hour is 3,600 seconds. So where are we now? We've done days, we've done hours. So now we have moles per second. That's a good place to start. So when I perform this arithmetic, I get 9.98 times 10 to the negative 6 moles per second. From the original half reaction, from the balanced half reaction, we know that each mole of C2HC3 requires 6 moles of electrons. So I'm going to start with my 9.98 times 10 to the negative 6, and this is moles of my trichloroethene. And that is moles per second. So I'm going to convert those moles of trichloroethene into moles of electrons. Then I can use my Faraday, 9.649 times 10 to the 4th coulombs per moles of electron. And you should come out with 5.78, that's coulombs per second, also known as an amp. Number 6, we have hydrogen ions that carry out useful work in a living cell, and that's fantastic. So let's get to the question, how many joules of work can be done when 1 micromole of hydrogen ion crosses a membrane and goes from a potential of a positive 0.075 volts to a potential of negative 0.090 volts. So we have a potential difference of 0.165 volts. Well, again, that question is how many joules of work? So we're looking at Q equals NF first. And that's going to give us, let's see, we have 1.00 times 10 to the negative 6 moles of our hydrogen ion. That is our 1 micromole. And we're going to multiply that by our Faraday, 9.649 times 10 to the 4th coulombs per mole. That's going to give us our coulombs. So Q is 0.964, and then I have more digits, but 9 comes after coulombs. So now our work equation is going to be capital E, so the voltage difference times Q. So the voltage difference was actually spelled out for you, 0.165 volts times our Q value, 0.0964, 9 coulombs, and you get a work value in joules of 0.0159 joules. Number 7, we're given the basal rate of consumption of oxygen by a 70 kilogram human. And that is 16 moles of oxygen per day. This oxygen oxidizes food, reduced to water, and it provides energy for the organism. That's fantastic. So, A, to what current does this respiration rate respond? So remember, current is going to be defined as a rate, and in this case, it's the flow of electrons from food to oxygen. So moles of oxygen per day, we have 1 mole of oxygen is going to consume 4 moles of electrons. And then we're going to have, let's say we need per day. So 1 day is, well, I'm going to go the long way. 24 hours, 1 hour is 3,600 seconds. So you should end up with 7.41 times 10 to the negative 4, and that's moles of electrons per second. Well, what does that do for us? Well, let's go back, double check the question. To what current does this rate represent? Current is coulombs per second. We have moles per second. So we need to take this 7.41 times 10 to the negative 4 moles of electrons per second, and we're going to multiply that by our Faraday, 9.649 times 10 to the 4th coulombs per moles of electron. So our moles of electrons cancel out. We're left with coulombs per second, and I get 71.5 coulombs per second, or amps. Now let's double check our sig figs. We have 16 moles. We have a 70 kilogram human, and that's a little bit ambiguous. I would take this down to 2 significant digits, I think, and we would round that because there is nothing after this 5. If there is nothing after the 5 on your calculator, round towards the even, call it 72 amps. If there is something, you again round up to 72 amps. And B, if the electrons flow from the reduced, what are we reducing? The NADH to O2, they experience a potential drop. So we have a potential drop of 1.1 volts. How many joules of work? So we need work is equal to EQ. How many joules of work can be done by 16 moles of oxygen? Well, we know the ratio here. So we have 16 moles of oxygen. 1 mole of oxygen requires 4 moles of electrons. 16 times 4 is 64 moles of electrons. Let's see, this is moles per day. I'm going to, again, take the long way because it's easier for me to keep it all straight. 1 hour, 3,600 seconds. So then, yeah, I didn't need to do that. I went too far. So 64 moles of electrons, and that comes into here, moles of electrons Now I'm going to multiply it by my Faraday. (9.649) times 10 to the fourth, and that's coulombs per mole of electrons. And then I'm going to multiply that by my E value, 1.1 volts, because this is Q, this is E. So you should get 6.8 times 10 to the sixth joules of work for number 7B.